Well, that was a real pleasure hearing Martin give that talk, and very apposite to the set of things that we've been discussing in the recent past in terms of clocks and in terms of the relationship between relativity and quantum mechanics. So it will be wonderful to have Martin here to take questions, but in his absence, I'm going to stand in for him and take any questions on that, and any questions or comments on that on that talk, everyone. Garnet.
I'd be happy to start if
go for it, Wolf.
If I can. Okay. First of all, yeah, I love this kind of presentations. I like his stuff for the main reason that he tries to include an environment. My basic question is that when, and especially like the idea when the box is vibrating. However, my question is, a vibrating clock would always include mass, real mass. And I'd like to, I mean, this is my general question always, is I would think that there must be a relationship between the motion of electrical forces, which always push some mass, which then always pushes the mass field. And I think there must be a cycle of interaction between electrical mass and the fields around them. In other words, that you have a four-phase system where charge produces fields, produces effects on mass, which produce effects on mass fields, which produce mass on charge. In other words, the whole thing is a charge mass or electrical gravitational cycle. And I think he's kind of shown that, except that he is still not including gravity. And I don't know, just open that as a conversation. And who was it that actually did this talk? I thought, Arnold, your name was next to the presentation the whole time. So
it's a recorded presentation of Martin's from a couple of years ago. So it was recorded at Vigier 2018. So anyway, Wolf, that's a very, very, very good question, and a very question very well put. Martin was giving the talk from a point of view of conventional physics. Of course, he was looking at just what would happen with a light clock, which is purely relativistic photon in a box physics, and then considering going a little bit further and thinking, okay, well, you know, if you have something going round and round and it's in some sort of box, watch the box. Now, what the talk didn't go into was what the box is, of course, or what the box might be. And what you said is precisely right, except for one thing. In my view, there has to be an interaction, as you say, between a four-component, at least a four-component system. Because if one's looking for a force, Martin was taking this as though the Poincare stressors were something unknown, and clearly they have to be there to make the box. Something has to keep the light going backwards and forwards. There has to be some system which is confining or making the system recursive, going around and around in circles. Martin was leaving that out in that talk. But if you, and in that case, you need a force to make the thing go round and round in circles or backwards and forwards, which in the case of a mirrored box are just the mirrors that are bashing it, and the material of the box holding it together is providing an internal confinement. But yes, if you want to go to something where you're considering the material of the box, I think that does have to be rest massive. It has to be, just as you say, it absolutely has to be a component in there which is rest massive. So in the talk I gave, which of course also stems from work between Martin and myself, where we're now looking within our theoretical view of how these things work, then that rest mass and the field are coupled to one another through larger set of equations than the Maxwell equations. And those larger set of equations include, in my case, a couple of mass terms, a couple of rest mass terms. These are rest massive fields, the pivot and the Quedge-Hogg for me. There are other ways of doing this. It isn't the only way, and of course it's not sure that my theory is the way the universe works. But it is sure that relativistic quantum particles are light speed, that a light speed oscillator does have those properties, and that we observe the de Broglie wavelength in relativistic quantum particles. All of that stuff is absolutely sure. Coming beyond that, one's in the realm of speculation. But if you want to go into something which is force-free motion, which is a natural motion, you do not need gravity for that. It doesn't have to be gravitationally confined. Gravity is far too weak. But if you look at my equations, dg equals 0 equation, the dg equals 0 equation, then the force term is coming from an interaction between the massive terms, and the massive terms are the pivot and the Quedge-Hogg term, which together form a subalgebra within the Clifford algebra CL13, which is isomorphic to the complex algebra. So there's a couple of things there which are like a complex massive wave, although they're more complex than complex in that they're embedded in something which is more fundamental. Between those two and between field terms being bivector terms, 6 of them, the electric and magnetic field. Now, the way Martin was putting those in the talk was he was saying that this is a modulation of epsilon and mu. And you can see it as being a modulation of epsilon and mu. In other words, that you're waving in space and space is waving. But you can also describe this in terms of a coupling, as you're saying, to a massive term, to a rest massive term. Now, for the simplest solution that I've found, the rest mass terms contain half of the mass energy of the system, and the field contains the other half of the mass energy of the system. In a single wave, in a 2-component, not a 4-component, but a 2-component wave function. Well, it's a 4-dimensional wave function, so it has, in a sense, it is 4-component, momentum and space, and energy and time, or frequency, of course. Wave function, which is oscillating with a pair of phases. These are the 2 phases of de Broglie, the harmony of phases. So there's a spatial frequency and there's a temporal frequency. And those spatial and temporal frequencies are exactly the spatial and temporal frequencies which Martin has calculated, of course, together with the fact that one of those spatial frequencies really is the zitterbewegung frequency of a relativistic particle, sum and difference. So you see, well, there are then 3 frequencies, of course, the sum and difference and the fundamental. So yes, there has to be a mass, but no, there doesn't have to be gravitation. Those forces are far stronger than gravitational forces. They are uber forces. They're forces which are stronger than strong. And they are the force which is at different levels giving rise to the strong force, which is what Viv was talking about last week, for example, in terms of this being a division by 0. You have things which are overlapping. In that case, you have fields which are cancelling. And that's an enormously strong force, because if you cancel a bit of something, to unwind it, you have to uncancel it. And that's a vastly deep potential well. So as soon as you start taking things and making them come back on themselves, they can turn around into a way where bits of them cancel. And once you've got that in a topological vortex, you have something which is not just stable, it's immensely strong, because you're sitting at the bottom of a very deep potential well. So the mass is there, and the mass has been crystallized into one of these particles by, you really shouldn't look at these things as forces, because they are things that must happen. It's not that there's some sort of resistance is useless to these forces. There is no such thing as resistance. It's a basic relationship between something changing, producing something else which changes. And that
okay, I give up. I give up. My hands are resistance is useless.
Absolutely. So this is a very, very, very strong force we're talking about here, not a gravitational one. So everything else you said is very perceptive and exactly 100% true. I don't think you need the gravitational side of it, but all of your other comments are spot on in terms of what's required there. Yes, I agree.
Well, let me just ask about, I mean, everyone always says gravitation is so small, but gravitation is associated with inertia. And inertia may be small on a small bit, but it is extremely strong because it involves the rest of the mass in the universe, which is huge. And it obviously is the force that balances the simple Bohr atom. So I'm wondering if we conceptually consider, instead of the box being a mass on the outside that contains the electric force. If we consider the mass of an electron as being the container, even though I know our vision is that it's a point somewhere, and how can that be a container? But it's an inverse container.
Both the container and its inverse, precisely.
Yeah. Then we could have a relationship between electrical and a container mass that is very similar to the equations we just saw, except the geometry is inverse. But it would be coupled to the rest of the masses in the universe through inertia, which then gives you a gravitational connection.
Once again, I agree wholeheartedly with everything you've said, except for that it's gravitational. Because, of course, that force is there, and the interaction with the rest of the universe is there, and it is enormous. The force on the surface of an electron, when you work it out, is roughly a Newton. And a tiny little thing like that, it's enormous. The current in the electron is 20 amps. You're talking about 20 amps of current going around a tiny circle at 10 to the minus 13 meters. Try and engineer that. We're talking about something which is immensely strong, and it is an interaction with the rest of the universe. And that interaction with the rest of the universe is responsible through Mach's principle for inertia, absolutely. But you see, when we talk about gravitation, we're talking about one force amongst a hierarchy of forces. Gravitation, electromagnetic, the weak force, the strong force, the super strong force, which is what I was just talking about. The electron, whatever's holding the electron together, is stronger than the strong force. Proof: take an electron, slam it into a strong force held together thing like a proton. Proton smashed to bits, electron unharmed. Badoom. That's how humans find out what's stronger than what, by banging the rocks together. Electrons are stronger rocks than proton rocks, obviously. I mean, this is ridiculously straightforward. So we're missing one of those things, but they're all the same force. We've got a bunch of forces there, but they're actually all the same force, Wolf. Now, you're absolutely right to say gravitation is thought to be weak, but it's related to inertia. Inertia is related to the rest of the universe. All perfect. But when you say gravitation is kind of like the weak brother of this whole set of five. Super strong, strong, weak, electromagnetic, gravitational. It's what's left over. It's what's intermediates. And that little, what we call gravitation is the weak bit. So I agree with you. I mean, I think these two forces are related, absolutely. But calling them gravitation is just messing with your mind, because you're calling something which is a leftover bit, and only the leftover bit, which is gravitation, to be the fundamental thing, which is really the super strong force, which is the other end of the scale. But yes, I think that once we get the ultimate theory of how everything works, then we'll understand why and how and what the relationship is between all of the forces. And in a future talk, I'm going to derive that relationship between electromagnetic and gravitational, and the size of them based on the size of the interaction with the rest of the universe. So I'm going to do that sum as well, but it is.
John,
Yep. Go on.
I got a question here.
Yep.
Do you have implicitly general relativity in your theory? Do you have implicitly general relativity in your theory? That's what it seems to me. Because the way you talk about it, even the last time when you mentioned that things are flowing, there's no force among them. That's exactly the way Einstein perceived space-time curvature versus the particle motion. And John Wheeler talks about how the space tells the particle to move and how the particle tells the space to bend. And when I was hearing Martin talking about it, light waving and vacuum and light, I was thinking, this is exactly what I had from the John Wheeler's talk, and then talking about what Einstein was talking about. The field exists, force does not exist.
Yes. No. General relativity is absolutely in there. But it's not in there. See, the way Einstein's putting general relativity in, he's putting it in as a curvature of space. He's putting it as a scalar curvature, as a piece of your space being missing. So that's a very simple way to do it. I think that general relativity is perfect as far as it goes, but I don't think it's complete yet, and it has to fit in with all of the others. Now, people are looking for quantum gravity and loop quantum gravity and so forth. I think they're looking in the wrong place. They should be looking where Wolf was saying just now, in the interaction with the rest of the universe, because Einstein in later life was also talking about the total field of the universe. These things are embedded in the total field, which is interaction with everything else. And what Peter was saying as well, when he's talking about the reflection of a particle in Mach's principle in terms of the rest of the universe, is absolutely right. Only half of the system is there. Only half of the system is here and now. The other half is far away and long ago. The interaction is, as Feynman and Wheeler were saying, between the emitter and the absorber at a point in space-time for each one of those interactions. So that's binding together far away parts of the universe in space and time. Here and now, the space and time we're living in is conditioned by the far away and long ago particles which constitute the universe in which we're embedded. So absolutely, regenerativity is perfectly in there. It's just the first term in a series. And Viv is later going to talk about looking at the next term in the power expansion for general relativity that is identical to general relativity at low energy, like any kind of energy pretty much up to black holes, and which differs in a higher order expansion in the next order. So yes, general relativity is in here. So the big question with general relativity is, what is the space and what does it mean to bend space? Now, up until now, we haven't had any answer other than a number. It's bent by this amount. It's just an amount of bending, and you put that in, and then everything comes out. But now we have a chance to say what's being bent. And what's being bent is, if you have a relativistic quantum particle, you have a little bit of space-time that's missing. That little bit of space-time is now a box. And if it's a box, there's the inside of the box and the outside of the box. And that bit of the box inside is the general relativistic bending. Exactly. It's a shadow for any other particle. And if you do the sums, then you get the right numbers. You get the 39 or 42 orders of magnitude, depending on whether you take the electron mass or the proton mass. You get the 40 odd orders of magnitude difference between electromagnetism and gravitation that everybody worries about. And I'm going to show that later. But yes, absolutely. Two superb theories, both of them absolutely calculable at both ends. General relativity on one side, absolute seamless contact. Quantum electrodynamics on the other side, absolutely seamless contact, except the new paradigm says how and why each one of those ones works. What is it that's the missing bit of space, and how does that work in terms of a piece of space-time being missing at the one end, and then at the other end, what is charge? Where does the charge come from? What's the nature? Why is it limited? Why isn't it infinite? I mean, in quantum electrodynamics, it is infinite. You put it in as an infinity, it's an infinity. The mass too. You get the physical mass and charge by renormalization, which is a nice mathematical trick, and it works because the charge of the electron is not infinite and its mass is not infinite. So if you renormalize to those things, then everything gives you these multiple orders of magnitude. But if you don't do that, then everything comes out infinite. But this tells you why that infinity is not, because the basic size of the electron is now the Zitterprovaging size. It's lambda c over 4 pi. And Dirac, even in Dirac's textbook, well, in the third edition of his textbook anyway, which Inga has, but I don't have a copy of it at the moment, so I can't show you. I've got the fourth edition here where it's taken out. He says that the cutoff you need to put in is lambda c over 4 pi. And then the numbers come out approximately right, as they do for a properly calculated electrodynamics without infinities. If you're going to chop off somewhere, lambda c over 4 pi is the place to do it. But this is why you chop it at lambda c over 4 pi. It's exactly that diagram Martin showed at the end, which is that size. It's lambda c over 4 pi in size. So yeah, absolutely. No, seamless starting points of general relativity and quantum electrodynamics.
Could I just make a couple of comments? Just well, first of all, thanks a lot for producing that. That was a real treat. I'd like to.
I was going to try and do that anyway, Garnet, for you, but yeah. It's so much nice to have Martin doing it because he did most of the actual work on that stuff. So,
well, it really was a real treat. I think it's right on the money. Just a couple of points. Wolf, the idea about gravity. You see, the thing that at least it strikes me, if you don't get to the place where I guess John and Martin are, which is to realize that in actual fact, quantum mechanics itself is a relativistic effect, then you're really out of luck with gravity and quantum mechanics, because you're coming from the wrong direction. If you're trying to quantize gravity, well, in actual fact, the relativity is underneath the quantum mechanics, and I think Martin's demonstration of that is pretty nice. But once you have that, then at least you have a starting point for basically looking at the two. And the idea of the Broglie wavelength and the being a beat frequency, when you just look at it from the point of view of numbers, if sort of just going back to the talks earlier in this series, that's the super strong force that John is talking about. I would just call that counting. Right?
Yeah, that's exactly what it is. It is. You have no choice.
It's just counting. When you throw away the reals and say, okay, if you're going to be the old curmudgeon, what's his name, Kronecker, saying this is all looking at large numbers. You see the things that come out are actually from the fact that you're starting with integers. You're starting with the discrete. And if you actually look at remember we sort of looked at the Dirac equation and said we're just going to have two choices. We're going to persist or switch, and we're just going to do the counting. When you do that, you see that really the only difference between special relativity and it's what people think of as an extension, being the Dirac equation. The only difference is where you start, and with special relativity, you already actually taken a continuum limit. That when you look at Dirac, in the end, you figure out what that continuum limit was, and it was the mass went to infinity. That's where you get to the continuum and the continuous world line. If you back out of that, then you're stuck with integers. And when you're stuck with integers, you have to say what you mean by the equivalence of inertial frames. And that equivalence of inertial frames is what gives you the difference between things like diffusion, where you think about masses of particles interacting and giving you all this peculiar behavior, and one particle that has images under inertial transformations. And that takes you right back to the statement itself, the equivalence of inertial frames. That's a massively powerful statement, because if you think of a two-dimensional space-time, you're filling that two-dimensional space-time with an uncountably large ensemble of particle paths. And so that is what actually this peculiarity of single particle quantum mechanics, that you have this wave that permeates space, but when you actually measure it, you come back down to one particle. That's because what you're implementing with the equivalence of inertial frames is that the equivalence over a whole space-time.
You're right, and that space-time has a very, very unlikely possibility that this eye will see that star. But the reason that uncountably small unlikelihood happens is because of multiple levels of division and multiplication. And at the level of division, when you're looking at the division on something which is relativistic, you're dividing by 0. So as you try and do your calculus d by d tall, you get an infinity, and that infinity means that anything can happen. You can communicate with anything at any different distance in that non-linear multiplicative system, which has an interaction. So looking at calculus now as a meta process, where you're looking at a process of d by dx, d by dy, d by z, d by dt. That's our x, y, z, and t. That's not the universe's x, y, z, and t. It's got lots of other ones. And all of them are operating. And once you realize that, you realize how incredibly small the universe is for light. And these particular interactions that take place are from A, very small, to B, very small, at least very small on the universal scale. And there's that connection. And what's happening is you're looking at this recursion, you're looking at this. What's the difference? It's exactly what you said, Garnet. It's exactly what you said. A piece of the universe is kind of missing in these things for you as you change inertial frame, because if you imagine moving inside our universe, you kind of lose part of the redshifted part of it. If you go very fast through the universe, you see the front half of it blue shifted and the back half red shifted. If you went very fast, you lose half the universe. There'd only be half of it there, but the stuff in front of it, the rest would vanish. And that process of losing half the universe is exactly this recursion you're talking about in terms of the twin paradox stuff. You're going tick tock in the rest frame, tick tock, and then you're going tick tock, and it's going and there's
like
no
heartbeat.
Yeah, it's like a heartbeat. Yeah, and that is counting the the counting, digitally counting, discretely counting the part of the universe which exists for one. So it's setting up those things which exist for any individual electron or human or planet or star or whatever. Yeah. So I think I just love how the stuff that you've done, coming kind of from the other way and finding this relationship, and then coming from the basis and deriving it in the first place, is sort of met in the middle. It's very beautiful.
Well, I mean, Martin's talk is so. To me, it's so physics. It's so like physics. You're actually dealing with these sort of things that are moving along, and you're looking at the frequencies and so on. The only thing that it's hard to see from that presentation is, I think, the where the algebra comes in, or where the Clifford algebra. But that's good in the sense that he's presenting you with a physical picture. You can follow the physical picture sort of from beginning to end, saying, oh yeah, well, we've made a mistake when we were looking at Schrodinger's equation, because Schrodinger's equation really isn't it. It's an approximation, and all of this stuff comes from special relativity. So you see that very nicely, and I think
that was done on purpose, Garnet, because we are having trouble, even more trouble than Peter's having with quaternions, with our CL13. So if we can take the Clifford algebra out of the talk, we will do.
Well, okay. So then I really must ask to have a fourth talk at some point soon, because there is a way where you actually see where the Clifford algebra comes from, and again, Kronecker would love it. It's just counting.
It is. However, I have a comment on that, which is that this talk has given you and all of us the relationship between the digital tick-tock of the clock, the time thing, and the continuous, the spatial continuity of the way that. So here you have both. You have both sides of that digital on one side of the hand, and the continuous on the other. There it is in the maths, with the transformations between them through the Vg equals c squared relation of what everything is made of, which is fundamental material, whatever that is. So but there it is. You've got both the continuous side of things, and the way that continuous side of thing changes, the frequency goes up, the continuous rate of change of phase goes up, which is just Pythagoras. It just gets a longer path. And on the other hand, the fact that the thing is going up and down in a cavity, there's some cavity. So wherever you choose on the cavity, if it's a circular cavity, the same thing, tick, 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 and that would slow down as well. So any kind of recursive system is going to have this feature of having this pair of frequencies that diverge from one another and produce a beat. So, the relativistic system is going to do that. It's not. You don't need all the machinery of the Clifford algebra to do that. Just you don't need quantum mechanics to build a rocket.
No, that is true. But the thing that I think has been a bit of a problem in the foundations of quantum mechanics is the misconception that you have enough in Schrodinger's equation to figure out where this stuff comes from. And in actual fact, you don't. Even when you have the Clifford algebra and have the Dirac equation, we've had the Dirac equation for nearly 100 years now, and still it's rabbit out of a hat.
But it is Garnet, but it's not just rabbit out of a hat. I now have my copy of Dirac. So it's not just rabbit out of a hat. I can show you where he made the mistakes.
Well, okay, but I guess my point is the thing that you don't get from most looks at the Dirac equation in quantum mechanics is what the heck the wave function is, right? Where does it come from? Why is there a superposition principle for the wave function and not a probability density? Well, if you can track that back. Here it is.
Page 265, 4th edition. I can tell you what's gone. I'll tell you what happened. And De Broglie pointed this out at the time. Look, this is a Dirac Hamiltonian here. P0. So there it is. It's got 5 terms. Can you see them, everybody? It's one with T.
Yeah.
Now, let me just read to you what Dirac then says. This equation differs from 30 through having 2 extra terms in the operator. These extra terms involve some new physical effects. This is Dirac, he's magnificent. But since they are not real, he means they're imaginary, he means they're square root of -1. Since they're not real, they do not lend themselves very directly to physical interpretation, he says. And then what he does is he throws them out. He does what my students do. They miss out the complex bit. And that's our Dirac. And then, but look, at least Dirac says it. If you read any other relativistic quantum mechanics textbook, they go straight to the Heisenberg equations of motion, which don't contain 2 of the terms. They're missing the complex terms. And then those have solutions which are complex solutions, but that one doesn't, and it never did. The solutions are put in from non-relativistic quantum mechanics. So what you do is you start, and this is the whole thing that has destroyed physics for so long. You assume there's a Lagrangian, you assume there's some phase term, you assume there's some action. And Wolf, we need to have a talk about action, because that was a fascinating discussion we got into the other day. I think, I don't know if you could lead it and give us a talk on that. That was a tremendous thing that we need to get into. Anyway, they have some action, but you're presuming the action is giving you a rate of change of phase in some wave function. But the wave function you put in is a complex wave function. You have just blown your mind up. You've just destroyed your possibility of ever putting in anything more than a commuting complex wave function. Now, complex is complex enough for most people, but it's far too simple. It's far too simple to describe what's going on when you have all these beats and this harmony of phases, and you have 2 phases. You can't describe 2 phases with 1 phase. You cannot describe the 3 oscillations with 1 phase. You're lost. You're already lost, and everything you do from there, and that's everything since 1950 for the entire physics community, you do from there is blind to that. Wow. So you've blinded yourself by forcing yourself to have what's essentially a non-relativistic wave function. De Broglie pointed this out. He said, look, Dirac's equation is relativistic, but the wave functions you're using are frame dependent. And they always have been. Every single one, in all the big books, in all the great papers, they're all bloody well frame dependent. That is so stupid.
Okay.
But it stems from that point. Now, look, the thing about Dirac is he's magnificent. It took me a long time to understand Dirac to get to the stage that I could start to. And when I first found the first mistake in Dirac, I just felt terrible, because he's one of my heroes. And I'm sort of looking at it and I think it must be me, and I'm sort of going backwards and forwards. And it wasn't until I met Peter Rowlands, who's found some of the same problems in Dirac, that I thought, my God, yeah, I'm not completely nuts. But the thing is that relativistic quantum mechanics doesn't work, because look what's missing. Look what he threw out. Look at the term that's gone. Here they are. This one's the magnetic field. That's the one he kept. That's the spin. That's half integral spin. What's the one he's thrown out? He's thrown out the electric field term. He's thrown out the charge term. It's the charge term that's missing. He's trying to describe an electron and a positron without the charge term. Forget about it. You're entirely wrong. And the reason we can't do it is because he's already a cryptographic, or at least a quaternion. So the reason they doesn't understand it is because it's not understandable within a complex algebra. It needs to be a Dirac gamma matrix.
Yeah.
It differs by it's the wrong guy. He's used I for 2 different things. At least 2 different things, I should say. But they're different I's.
Right. Well, if I was Chronicle right now,
question in here, because as a physicist, you know, I love this last presentation. In fact, I like Martin's presentations. I always like him because he is much more physical. But has anyone, or has he looked at, given the fact that this light clock now has a potential to interact with the rest of the universe through its breathing, what about 2 light clocks? Has there been an analysis of having 2 light clocks interact, and what would be the interaction between them? Because they probably do resonate.
Yeah, they do. That was my talk on quantum collapse a couple of 3 weeks ago, Wolf. So I don't know if you've had a chance to look at that yet, but yes, they do interact with one another. And what they need to do is have an interaction. The interaction, just briefly, that interaction is through a field. It's from point to point. So there are strong constraints on what the shape of the field needs to be. Pretty much that it's a line between the 2 points, quite close to that. It's from point to point. But given that limitation that it has to go from A to B, from 2 points, 1 point in the universe to another point in the universe, it's an inversion. It's a total inversion. And it has to be an inversion because only an inversion of a field is going to give you a scalar exchange of energy. Now this is part of where we were in that discussion between you and I and Peter the other day that we need to take further in terms of action and what's exchanged. Is it energy or is action the thing that's that's intermediating something? And it's a very, very big discussion that we need to have with the whole of the physics community, because I think it's a place where there's a huge amount of confusion, and well, it's also the cutting edge of physics, so of course there's going to be a lot of confusion there. So, but I think that's something that we in Quicycle can throw a lot of light on. We have the people we need to do that kind of thing, and nobody else does, and nobody else ever has. So this is what we are for in terms of sorting this out. But it's an inversion. So if you have an inversion of any complex distribution, which is not scalar, which is fields, it could be currents, it could be angular momenta, but it's got all of those elements to it. The only way to find something which takes something which is 16-dimensional, if you like, or 16 degrees of freedom, and it is to find the inversion for that whole thing. So you need something which is both the inversion of a field. What's an inverse field? Well, okay, that's but that was worked out by Martin as well, and is in that talk a few weeks ago. But then also the inversion of space. How does the inversion of space work? Well, we've known that for a long time because we've been able to do. We know that if you have any coordinate system, the inverse coordinate system is a conformal system. It's one which also supports the Laplace equation. Any kind of differential equation of the second order is also supported in the new system, because a small box transforms to essentially because a differential box transforms to another differential box. Right? So it's a conformal transformation. So, but that conformal transformation, that particular one, is the one that leads to a scalar. So you have your fields, but you also have the inverse field, and field times inverse field is 1. It's a scalar, and that's the interaction. An interaction requires energy to jump, a scalar object, scalar stuff to jump from A to B. Clunk, click, has to go from A to B, and for that you need an inversion. So the basic operation is inversion. But if you don't have all the bits, if you throw away the electric field part, what are you inverting? You're never going to find out what's going on. You cannot, because the inversion involves the whole field, not just bits of it. But that's where it went into the mist, as we hard to mist in Dutch. You go into the mist. And I don't spell mist here, M-I-S-T. We get Scottish mist, which is spelled M-I-S-T. This is M-Y-S-T, which is mysticism and mystery and mystified. And you get into the mist. And as soon as you're in the mist, you can't get out because you can't see anything, because you've already destroyed your eyes. You've already taken out the possibility of seeing what you need to see.
Yes, so the correct spelling is actually M-I-S-S-E-D.
Yes. Got it. Precisely. The missed opportunity. Good for you. Yeah. No, but it's but it's do you know what the really beautiful piece of work is here? It's really De Broglie. It's really De Broglie in the first place. That was a feat of imagination and a feat of an intellectual leap forward of the highest degree. This is 7 years before the Schrödinger equation, gentlemen, ladies. It's tremendous imagination, and to find that there are two oscillations which are everywhere and for all time in phase, and yet at different frequencies, they move through one another seamlessly because of the Lorentz transformation. It's magnificent. And that's what gave Lambda's H over P, and that's what gave wave mechanics, the wave mechanics aspect of quantum mechanics, because what you do then is you assume you have a complex wave function and you pull down the momentum through a differential, and then you have the differential equipment to generate wavelengths and frequencies from your wave function. And that's beautiful, but it's not beautiful enough. It's very beautiful, but it's only a part of the beauty of the whole thing that's underlying it. And until we get fully quantum relativistic wave functions, and they are up there. I've put them up. These things transform relativistically, and they transform through Peter's nilpotence because they tie different bits of the wave function together. They are self-referential wave functions that are fully relativistic. Photon wave functions, they're up on Quicycle already, just waiting for people to realize what it all means. But it's not hard to. It's not easy to understand all of this at once, of course. So, but that's what we need. We need relativistic wave functions, and they've not been around for long. I think the first time I presented them was 2014, but nobody's taken the blind bit of notice.
Aren't Peter's wave functions relativistic? I mean, he uses these nilpotent 5-term entities, and then a lot of times he considers one to be the operator and one to be the wave function, and it looks like it's automatically relativistic.
It looks like it, and you do fool yourself on that, but no, the wave function is still a complex wave function that he's using to pull those things down. So while you could write down a fully relativistic nilpotent wave function, those are not yet it, because they don't have
But I mean, what he's already done is he's pulled it down, but he basically puts that into the amplitude. You know,
that's right. It's in a particular frame. It's still in a particular frame. Not to say that it can't be done, because well, of course it can be done, but they are not yet the whole story. Although they're a very big part of the story, of course. But I think the only way.
I'd love to give a talk, but I'm going to have to get involved with Arnold a little bit because I'm scared of running this system. I know how to push a few buttons, but actually making a talk in this system is still a mystery to me. So. And a bigger mystery than physics, frankly, at this point.
Well, Wolf, you need to educate yourself on that, because we want to hear you speaking at some point in the not too far distant future. So I'm very interested in getting more deeply into looking at the observer and the effect that has. And I think you're the best person to take us forward on that one. So I'm looking forward to that talk at some point in the not too far distant future. So grab Arnie and spend as long as you like. And it's not very hard, actually. Once you press the button, you can just talk. So it's not so bad. So
okay, well, Arnold, maybe I'll get in contact with you, and then we can do a practice session so that I feel comfortable.
My pleasure. Anytime, no problem.
All right, great, thank you. All right, my wife says I got to go, so bye. And this was a great talk. Thank you all.
Thank you, Martin. Cheers, Wolf.